This is the beginning of the lecture on section 3.1, Introduction to Determinants. The word determinant plays a big role. The concept of determinant plays a big role in linear algebra. So let's get started talking about determinants. And notice in the first line we say to every square matrix we associate a number called the determinant of A, and denoted DETA. Just want to make a point here that just realize that here are a couple more sections, 3.1 and 3.2, where only square matrices are going to be involved. So just like the idea of inverse matrix only applies to square matrices, the idea of determinant only applies to square matrices. So the determinant is a number associated to a matrix. Every matrix has this number associated to it. If we have a 2 by 2 matrix, it's easy to say what that determinant is and what that number is. And many of you are probably familiar with this idea with 2 by 2 matrices already. We just take the product A11, A22 down the main diagonal, and we subtract the product we get by multiplying the entries on the reverse diagonal. So here's an example. If A has entries 4, 2, 3, 5, the determinant of A we get by taking 4 times 5 is 20, minus 2 times 3 is 6, 20 minus 6 is 14. 14 is that number called the determinant. Now, a technical point about notation, and try to be careful about this. When we put square brackets around an array of numbers, that refers to a matrix. But when we use these straight line bars, looks kind of like absolute value bars, that has a different meaning. That means we're calculating a determinant, and so that's equal to the determinant, equal to just a number value. Defining the determinant for larger matrices is more complicated. And here we go. Let's start talking about that. So let A be an n by n square matrix of any size. Now we're going to define this creature called capital Aij. So this is capital Aij. This is different from little aij. We're not just referring to an entry in the matrix. Capital Aij is a matrix obtained by deleting the ith row and jth column of A. Aij is called a submatrix of A. So it's easy to see from examples what this is all about. So let A equal this matrix that I just made up. We can talk about A11, so capital A11 is the matrix we get by removing the first row and first column of A. So we're left with a 2 by 2, 0, 8, 9, negative 7. A23 is the submatrix we get by removing the second row and third column. So take the second row out of A, the third column out of A, we're left with 1, negative 3, 4, 9. And think about what A32 is. So again now, let A be an n by n matrix. We're going to define what's called the ij cofactor of A. So this is going to be a number. It's a number denoted Cij, little cij, such that Cij is equal to negative 1 to the I plus j power times the determinant of the capital Aij submatrix. Whew, quite a mouthful. We'll see from examples that this isn't all that bad. So back to our example above, let's compute some of these cofactors. So the 1, 1 cofactor of A is denoted C11. So we're going to take negative 1 to the 1 plus 1 times the determinant of A11. Now negative 1 to the 1 plus 1 is negative 1 squared, which just turns out to be 1. So notice this power of negative 1 is always going to be either negative 1 or plus 1. So it'll either change the sign of what we have if it's negative, or leave the sign of what follows the same if it's a positive 1. And then the determinant of A11 we can just calculate from, we get 0 minus 72, right? It's negative 72. So we take 1 times negative 72 is negative 72. The 2, 3 cofactor of A, C23, is negative 1 to the 2 plus 3 times the determinant of A23. So here, I think we can kind of see that if the subscripts add up to an odd number, we're going to get a negative 1 to an odd power, which will be a negative 1 factor. If the subscripts add up to an even number, then we'll only end up multiplying by positive 1. So here we get negative 1 times the determinant of A23, which is up here. That's going to be 9 minus a negative 12. 9 plus 12 is 21. Negative 1 times 21 is negative 21. So we have this idea of cofactor, the IJ cofactor. Now we're going to go back to A as an n by n matrix. The determinant of an n by n matrix can be computed by what we're going to call cofactor expansion across any row or down any column. If we use the ith row, then the determinant of A is going to turn out to be equal to, now look at this sum, I don't even want to read it, but we're taking entries of the ith row, so this is little a, I1, times this cofactor number, plus the next entry in that row, times the corresponding cofactor number down the line. We could also use the j'th column, and then we would do a similar kind of thing where we would go down a column and add up products as indicated here. Determinant of A will come out the same no matter which row or which column we choose. This is not at all obvious. So we will consider the statements above as our recursive definition of determinant of A, even though the textbook calls this theorem 1. Now, what we're not going to be able to show is why all of these different possible ways of calculating the determinant always come out the same. That gets a little bit beyond our scope here. And also, I just want to say there is a formal and elegant and beautiful definition of determinant of A that involves permutations. We're not going to study that definition. If you want to know about it, just contact me. I'd be happy to go on and on and on and on about the definition of determinant of A using permutations. Another note, this is really important, the negative 1 to the I plus j factor in all of these calculations is easy to keep track of if we keep in mind a pattern of plus and minus signs in a matrix. So this is what it would look like, the pattern would look like in a 5 by 5 matrix. The entry, the A11 entry, I put a plus sign there because 1 plus 1 is 2, negative 1 squared is going to be plus 1. The next entry over is like A12, 1 plus 2 is 3, negative 1 to the third is negative 1. Next entry over, the subscripts are going to add up to an even number again, so negative 1 to an even number will be positive, so on and so forth. And when we go through an example, we'll be able to use this pattern, and we'll talk about how it works. So I think what I'm going to do is I'm going to leave the exercises where we do some calculations now for our next video segment.